Thank you, Rick, for the presentation. Thank you for allowing me to speak at this category theory Oktoberfest. Unfortunately, this talk is not a talk in category theory, but rather is a talk about a specific category, namely the category of separated metric compact Hausdorff spaces, which we will see are certain compact Hausdorff spaces equipped with a metric. And this category is an approximation of the category of compact metric spaces, but it's much better behaved. So, so I hope that studying these examples also gives food for applications of the theory and possibly some insights to develop the theory. And from the beginning of our research on this topic, of me and Dirk Hoffman, we we knew that this might have a generalization to a larger setting, even especially because we were motivated by the fact that the main result I'm going to present is an adaptation from the order setting. So if instead of taking metric, you take the order setting, this result was already known. And so most likely these results have also a generalization to a richer setting, probably to a quantale enrichment setting for certain quantales, as we know from Lawvere that metric is similar to order. And well, it would be amazing if one can go also beyond quantales. So quantales are special symmetric strict monoidal categories. But this is out um, of my field of competence now. So in this talk we will focus by design on this specific category, this category of these compact Hausdorff spaces equipped with a metric. So to keep the intuition from the metric setting. Okay, so let's see some historical background. Okay, we know that compact Hausdorff spaces are the Eilenberg-Moore algebras for the ultrafilter monotone set. So the category of compact Hausdorff spaces and continuous maps is a variety of infinitary algebras, so it has an algebraic flavor. For example, it is Barr-coexact. Okay, but besides the algebraic flavor, it has also a topological flavor. And usually the opposite of a category with a topological flavor has an algebraic flavor. For example, while top, the category of topological spaces, is not regular, its opposite is regular, and in fact, even a quasi-variety of infinitary algebras. Or the opposite of the category of those spaces called the stone spaces is a variety of algebras, namely Boolean algebras. This is the famous stone duality. So the opposite of the category of stone spaces is monadic over set. So any monadic functor of a set is representable by the free algebra on one generator. And here in this case, if you want to skip Boolean algebras and start directly from stone up, this functor is represented by the two-element space 0, 1. Okay, but now if we take this monadic functor and we tweak it a bit, and instead of stone spaces, we take compact Hausdorff spaces. And here, instead of the two-element space, we take the unit interval. Okay, then we get a monadic functor still. So not only CompHaus is an infinitary variety of algebras, but also its dual is such. So it's monadic over set. So its dual has an algebraic flavor, which means this functor being monadic means that is a way to collect certain categorical properties of CompHaus, namely that it's complete, it's cocomplete, is Barr-coexact, and that 0, 1 is a regular injective and a regular cogenerator. Being a regular cogenerator, for example, is not just a nice categorical property, it amounts to Urysohn's lemma, which is one of the main results in topology. Okay, so from these proceedings in our historical overview, one can add order. So stone duality has an important generalization to, to the order setting, which is called Priestley duality. Priestley duality is a duality between, on one side, bounded distributive lattices, which are important in the algebraic treatment of logic, and on the other side, Priestley spaces, which are stone spaces equipped with a partial order satisfying certain properties. And again, here we have a monadic functor from the opposite of the category of Priestley spaces to set, and it's represented by the two-element chain in this case. Okay, so the previous result on stone spaces generalizes to the ordered topological setting. And now we come close to the present, where Hoffman, Neves, and Nora had this question where we can see four squares. We know we have a compact Hausdorff setting where we have a monadic functor represented by 0, 1. Also in the stone space we have something similar. Here there's an error, it should be the two-element space. And also here in the setting of stone spaces together with an order, we have a monadic functor. Well, and they asked, okay, is there something similar here in the compact Hausdorff plus order setting? And in fact, there was already a notion of compact Hausdorff space together with a compatible partial order, which goes back to Nachbin in the 40s. I will not give the motivation, the precise definition, but the one recent result is that this monadicity story goes through also this setting of compact Hausdorff plus order. So if you take a certain category of Nachbin spaces, I mean the category of these Nachbin spaces with continuous order preserving functions, and we consider the functor represented by the unit interval, this is still monadic. And again, here, this result is also a way to compress, to present some categorical properties, nice categorical properties. For example, well, precisely, completeness, cocompleteness, the fact that 0, 1 is a regular injective regular cogenerator, which was already observed by Nachbin, not in categorical terms, but rather what this means. And the fact that Nachbin is Barr-coexact. Okay, so in conclusion, we already had these results both for compact Hausdorff spaces and its ordered version. And now we get to separated metric compact Hausdorff spaces. Okay, and so from Lawvere, we know that order is similar to metric. So the question Hoffman and I asked ourselves was whether there's an analog in the metric setting. And now for this, we need the notion of separated metric compact Hausdorff spaces. But, well, in order to advertise also these structures, let us see some drawbacks of the category of classical compact metric spaces. So there's a category of these metric spaces whose topology induced is compact. If you take as a morphisms non-expansive maps, this category is not cocomplete. There is not even a coproduct of two singletons. And the remedy here is to allow the distance infinity. And it's not complete as well. And here the remedy is to allow the topology to be just compatible with the metric rather than induced by it. Okay, so for this talk, a metric will be a map from x times x to 0 infinity which is reflexive, so the distance between x and x is 0, and satisfying the triangle inequality. Right? And it's called separated if the distance between x and y in both directions is 0, implies x equals y. Now, if you like also to add the symmetry axiom, one can, and the main result I'm going to present will still hold. But it's not needed, and moreover, if you omit it, then we see better the connection with order setting. One way to see it is that if D is only allowed to take values 0 and infinity, then a metric is the same thing as a preorder, where the distance between x and y equals 0 means x less or equal than y, whereas separated metric means partial order. Okay, now this interesting structure. So separated metric compact Hausdorff spaces. These are compact Hausdorff spaces equipped with a metric which has some compatibility. What is the right notion of compatibility? Well, lower semi-continuity. What does lower semi-continuity means? It means that if we have two elements, x0 and y0, and we approach it from close by, topologically close by, then the distance between x and y, if I take the limit as x and y tends to x0 and y0, the limit will be greater or equal than the distance between x0 and y0. So in other words, small topological perturbations may yield great increments in distances, but not great decrements. Or in other words, it means continuous with respect to the upper topology, the one generated by these subsets. Let us see some examples. Well, first of all, any compact metric space is a separative metric compact Hausdorff space. So this class of structures give an environment in which also this classical structure live. Zero infinity itself with the usual compact Hausdorff topology on it, and with the distance given by the difference between B and A, if A is smaller than B, or 0 otherwise. Or as another example, for any set X, if I take the product, X full product of 0, 1, with the product metric, which is also called the sup metric, and the product topology, this will be a separated metric compact Hausdorff space. And yes, in general, this metric will be lower semi-continuous, but not continuous in general. Or the other way around, the topology is not induced by the metric. Okay. Another way to motivate that these structures are natural is that metric compact Hausdorff spaces are the algebras for a certain monad. So a metric version of the ultrafilter monad. So it's a monad on the category of metric spaces and non-expansive maps. For more details, I suggest to look at these references. In particular, here in Hoffman and Rice, they build such a monad for any quantale. Here we are only focused on metric structures. Okay, but I recommend these readings. Okay, now defining the category of separated metric compact Hausdorff spaces and non-expansive continuous maps, as let us denote them by MET-CH SEP. The question was whether the contravariant representable functor, represented by 0 infinity, is monadic. Okay, so this is a direct generalization to the metric setting of what we knew hold for the order setting with Nachman spaces. And can be this turns out to be equivalent to asking these three questions. Is METCH SEP complete and cocomplete? This was known to be true already. Our main result is an answer to the second question, so whether this category is Barr-coexact. And this is true still. We'll see in a moment in concrete what this Barr-coexactness means for this category. And finally, the third question is whether this zero infinity is a regular injective regular cogenerator. And this is left for some future work. Okay, what does this Barr-coexactness means in concrete? I'll have a few slides about this. So let's proceed in step. This category has epi-regular monofactorization, where epi are surjective morphisms and regular monos are embeddings. And this factorization essentially just it keeps the image of a morphism with a subspace topology and subspace metric. And moreover, this factorization is stable under pushouts, so it's quite well behaved. This category is coregular. In concrete, this means that if I have an embedding and a morphism from the subspace K to K prime, then inside this X, on which I have K, I can replace, instead of K, an exact copy of K prime, and with some possible adjustments outside X. Maybe the distance between elements here changes. Okay, but inside we get an exact copy of K prime. This essentially is coregularity. But even more, it's Barr-coexact. In this case, what does it mean? It means that, well, first of all, notice that if I have a separated metric compact Hausdorff space X, so I have this space equipped with a compact Hausdorff topology and a compatible metric on it, and I have a closed subset, okay? Then if I take two copies of X, this subset K induces a quotient of these two copies just by gluing the two copies pair by pair of K. So we get something like, I don't know. We get some gluing. In Barr-coexactness, it says that if I start with a surjective morphism from X plus X to some Z, and if it satisfies three conditions, coreflexivity, cosymmetry, contransittivity, I will not go into details of what these are, but these are first order conditions. Then I can get this higher order condition, which is the existence of a closed subset K such that this surjective morphism is precisely gluing at K. So from these first order conditions, I get this existence of a subset K. And here compactness is crucial in doing this. Okay, so, well, to sum up, here we focused on this particular category of separated metric compact Hausdorff spaces and continuous non-expansive maps, which is a nice approximation of the category of compact metric spaces in the classical sense. And here we continued the work of showing that this indeed is quite natural and quite well behaved. the question motivating for us was whether this functor is monadic, the representable contravariant functor represented by zero infinity. And in particular, a contribution is to show that it has the opposite has an algebraic flavor. In particular, the opposite is Barr-exact. And for future work, we will address whether zero infinity is a regular injective, regular cogenerator. So, for example, being a regular cogenerator is also something interesting outside its the analysis of the categorical properties. Namely, it amounts to a metric version of Urysohn's lemma. Okay. Thank you for your attention.